p/poly, p space/poly.
Yes, thank you. Do you hear me? I'm not sure if this is working.
It's okay. Not for recording.
Yeah, but okay.
It's a little bit much.
So hopefully it's okay.
If you want us to hear, speak to that microphone.
So I should look like that.
No.
I think I'm fine. This has a red light. Yeah, first of all, I'd like to thank the organizer for inviting me here and for arranging this CCR edition in this very inspiring setting. I'll talk about language compression. The announced title was compression for sets in p-poly, but the technique is very general. It works for a lot of complexity classes. This is based on a paper that I presented last year at FCT. So what's new? Well, nothing is really new. The proof technique is a little bit simplified based on a suggestion of Vinod Chandran. And also I noticed that the technique also works for non-uniform classes like p-poly and p-space poly. So what's the language compression problem? So to motivate, I will just remind you a very simple and basic and very useful fact from standard Kolmogorov complexity. If A is any computably enumerable set, and then for every string x in A of length n, the Kolmogorov complexity of x is bounded by log of the size of the strings of the set of strings of length n in A plus accuracy term which is pretty small, order of log n. And this is a very basic and simple observation. It follows just because x can be described by its index in an enumeration of the strings of length n in A. And the question, because enumeration is slow, is whether there is a time-bounded version of this fact. And when we look at time-bounded, the focus should be mainly on polynomial time bounds, because again, by the same easy observation, for every set A, for every string x in A of length n, the complexity of x, if we allow the universal machine to have access to A, is again bounded by log of A to the n plus order of log n. Again, x is described by an index in among the elements of A to the an. And this can be even done in exponential time with respect to the oracle A. So the question here is whether there is a polynomial time version of this. Okay, so now if we look at resource-bounded Kolmogorov complexity, there is a variety of ways to define that. First of all, if we focus on polynomial time computations, there are different kinds of computations. It can be the standard one, which is deterministic, but it can also be non-deterministic polynomial time or probabilistic polynomial time bound, probabilistic polynomial computation, or even a combination of non-deterministic and randomization. So the version that is used for this problem is the distinguishing complexity introduced by Sipser in 83. And informally, the distinguishing complexity of a string x with time bound t, denoted cd t of x, is a length of the shortest program that accepts x and only x, and in time bounded by t of x. Okay, so formally, this is the definition. CDT of x is a length of p, where p is the shortest program such that after we have fixed a universal Turing machine u of p and x accepts, u of p and y rejects for every other string other than x, and u of p and y halts in at most t of y steps. Okay, so this P can be thought as being a fingerprint of X, so that X can identify itself efficiently using this P. Yes. And as I said, we can allow variations of this. We have a CDTA of X if we allow the universal machine to have access to the set A. I will briefly mention also this version. CNDT is when the universal machine is non-deterministic, running in polynomial time. That's an interesting case. CAMD is when the universal machine is a so-called Arthur-Merlin machine, basically meaning that we allow it to use both non-deterministic steps and randomized steps. CBPD is a version where the universal machine is randomized and runs in polynomial randomized time. So this problem has been studied before, and I will summarize what is known. So first of all, there is this very general result of Berman, Fornow, and Lapland. They show that for any set A, for every x in A, CD poly of x is bounded by 2 times log the size of A plus that accuracy term order of log n. This is very general, but it is not optimal because of the factor 2. Information theoretically would hope to get just log of A of n. However, in the polynomial time setting, the 2 is necessary. This was shown by Berman, Lapland, and Milterson. So they have exhibited some examples, some sets A for which Z factor 2 is actually needed. We cannot compress better than Z. On the other hand, if we allow non-uniformity, for example, we can get optimal compression. So there is this old result of Sipser. For any set A, there is advice information of length polynomial in n. So for every string x of length n, there is a polynomial depending on the set A, so that CD bounded with that polynomial of x, given that advice information is optimal, yes, is bounded by what we are looking for. So this is if we allow the universal machine to use some non-uniform information, yes. So that string W only depends on the length. If we allow some error, again we can get optimal compression. We have this result for every A, for every epsilon, which measures the error. For every x, again we get optimal compression. And the accuracy term is bounded by polylog n. What else? If we allow the computation, the distinguishing program to be non-deterministic, then again we can get kind of optimal compression. The CND, so this is a version of distinguishing complexity where the universal machine can use non-determinism, bounded by polynomial time, is again bounded by log n, and there is this accuracy term, which is so the dominating term here is this one, but this is it's a little bit better than the order of log n. If we allow both randomization and non-determinism, we can get better. So this is the dominating factor, which is or term, which is what we are hoping for, and this is the accuracy term. On the other hand, if we only yes. Yes, so this means that the universal machine is following an Arthur-Merlin protocol. Well, the definition is a little bit technical, but basically it means that we allow both non-determinism and randomization. Yes. On the other hand, if we allow only randomization, then again we have this factor 2. So there are some sets for which we cannot do better than 2 times log. So this is an extension of the Borman-Laplace-Milterson results that I mentioned in the first slide. Okay, so what I'm looking at in this work is I'm looking at the problem from a different angle. So instead of changing the type of computation, I stick to just polynomial deterministic, the standard type of computation. But I ask for what sets can we get optimal compression? Yes, meaning this. And the answer so far is that, of course, using some assumptions, because this is complexity theory, we cannot do much without assumptions. We can get optimal compression for sets in p-space poly. But the assumption is different for each complexity class. But all of them are reasonable. So this is the strongest result. Yes, I'd say. Okay, so I will sketch the proof for the case when A is in p poly. And as I said, what I'll show is it's an improvement of a method that from my work from last year. Chandran is spending his sabbatical in Baltimore, and we have a seminar at College Park, and we are carpooling, and every Wednesday, of course, it's a 45-minute drive. We talk about theorems and proofs, and this came up during such an occasion. The proof that I used last year had 2 steps. So there is a certain search space that has to be reduced 2 times. And there is a step 1 for the first reduction and the second step for the second reduction. Step number 1 last year used non-explicit extractors, which were then made partially explicit using Nixon pseudo-random generator based on an idea of Romashchenko, Musatov, and Sasha, and Kola. And then the second reduction is using Nissan-Wigderson pseudo-random generator. The simplification is that the first step was replaced by something much easier, you'll see. Okay, so again, I'll do the proof for A in p-poly. So what is p-poly? P-poly is a class of sets decidable in polynomial time with polynomial advice. It's an important class because it is the same as a class of sets computable by polynomial size circuits. Okay, so we take a set A in p-poly, and we fix a string x of length n in A. And we let k be log of the size of A, so the size of A is 2 to the k, let's say. And suppose we find a function h that maps strings of length n to strings of length k plus 1, which is polynomial time computable given h bits of information, which isolates x in A. Isolates x in A means that h of y is different from h of x for all the other y's. So the pre-image of h of x has just one element, which is x. Okay. Then we can notice that h, this function, and the image of x, h of x, distinguishes x among the strings in A. So therefore, the CD complexity of x is bounded by k plus 1, which is the length of h of x, plus the length of the function h, plus we need some additional order of log n to describe n and concatenation and some other simple stuff. So now to finish the proof, I need such a function h, which can be described with log n bits. Yes, because in that case, this will also be order of log n, so I will get what I need. Yes, it will be merged into an order of log n term. Okay, so this is a problem. I want a function h from n bit strings to k plus 1 bit strings that isolates x. And h can be described with order of log n bits. So how do you find such an h? Well, usually when you look for something, you just pick it randomly. Usually this works. And indeed, if we choose the function h randomly, then clearly the probability that h of x is equal to h of y for a fixed y is 1 over 2 to the k plus 1. And there are at most 2 to the k strings y different than a, so by a simple union bound, the probability that h does not isolate x, so that there is a y, so that h of x is equal to h of y is bounded by 1/2. So it means that if we take the function h randomly, with probability of more than 1/2, h does a job. H will isolate x. But the length of h is 2 to the n times k plus 1, which is double exponentially longer than what I want. So I have to reduce it 2 times. Yes, remember, I want h to have order of log n bits. Okay, so the first reduction is based on the observation that for the probabilistic argument, I don't need the function to be completely random. I only need 2 y's independence. Yes, because yes, I only need this relation here, and this works if I have only 2 y's independent. So therefore, I can take h to be a simpler function. I can take it to be a linear function, random. Basically, this is a k by n matrix. It is well known and very easy that h is 2 y's independent. And then with the same argument as before, with probability more than 1/2, h isolates x. And now the length of h is n times k, which is still not what we want, yes. We want to reduce it one more time to order of log n. So far we have reduced the length of h from 2 to the n times k plus 1 to n times k. But again, that's not enough. So for the second reduction, here I need an assumption, yes. The second step will use a pseudo-random generator. So what is a PRG? Well, that's by now very well known in complexity, but for people not in complexity, I will remind. A PRG that fools a class of sets C is a function that outputs strings of length m from a set having length logarithmic in m, which is computable in polynomial time in the output length, such that for every set in the class of sets that we are fooling, the probability that g of s is in B is close to the probability that a uniformly distributed random string is in B. So this means that no set in C can distinguish between the output of G and a generally random string. Yes, we are saying that G fools the class C. Okay, so now going back, let's look at the function, the space, search space that we have reached so far. We are looking at the functions h, which are linear, mapping n bit strings to k plus 1 bit strings that do not isolate x. I look at the complement of what I want. This set is in NP poly because I just need to guess a string y that maps into the same image as x. And because A is in P poly, B is in NP poly. So I need a PRG that fools NP poly sets. because in that case, that PRG will also fill this particular B. Now the complement of B is large, because more than half of the functions are in the complement of B. So this means that for almost half of the seeds, G of S will be also in the complement of B. So for some seed X, actually for many seeds, for almost half of them, G of S will be a linear function that isolates X. And now the length of this S, which describes S, is just order of log n, which is what I want. Okay, now how do we get the PRG? Well, this by now it's well understood in complexity. It's one of the big success stories in complexity. So we have to start with a function computably E, which is hard. And how hard? Well, it depends on what class of sets we want to full. In our case, we want to full a set in MP poly. So to full this, it has been shown that we need the hardness of F to be, we want F to not be computable by circuits of size 2 to the epsilon n for some epsilon, having also a special gates which are SAT gates. How do we get such an F? How do we get an PRG from such an F? Well, that's a long story, but it's well understood. One can see that the output of S is already somewhat unpredictable, but this does not mean that it is a PRG. Using some clever ideas due to those people, from such an F, one can build a PRG that fulls all the set in MP poly, which means that this is the assumption that we need. Yes, we need a function F computable in E that for some epsilon cannot be computed by circuits with SAT gates of size 2 to the epsilon n. And if we have this assumption, then we get a PRG that fulls MP poly, and this means that sets in P poly can be compressed optimally. So this is the result. Yes, under this assumption, any set in P poly, for any set in P poly, there is a polynomial P, so that CD with time bounded by P is optimal. And the same technique works for other complexity classes. We only need different assumptions. The largest class here is P-space poly, so let me just show the result corresponding to P-space poly. We need this assumption. Actually, we need something weaker, but that's too technical, so I prefer to write down this one. So the assumption is that there is a function in E, computable in exponential time, but not in B space 2 to the little o of m. That's a reasonable assumption. And with this assumption, this assumption implies that any set in P space poly can be optimally compressed in polynomial time. Okay, so just a few final comments. Pseudo generators have been used before in resource-bounded cosmograph complexity. I will just cite these two results. The first one is by Antunes and Fornau. They showed under a similar assumption that this distribution is universal among p-sampleable distributions, meaning that for any p-sampleable distribution, there is a polynomial p such that the cosmograph complexity of x with time-bound p is at most log of 1 over sigma x. Yeah, this is a polynomial version of the classical Levin and Gach result. Also another result by Antunes, Fornau, Pinto, and Souza about computational depths is also using PRGs and assumptions, similar assumptions. So perhaps the morale from here is that this is a way to go if we want to extend classical results to polynomial time-bounded cosmographic complexity. It seems that we need this kind of tools. And yeah, I'm pretty much done. Okay, let me show you how to show that P is not NP. Well, to show that P is not NP, what we need to do is to just find a set A, so that for some string x in A, the CD complexity of x in polynomial time with oracle access to A is greater than 2 times log A. And we know how to get such set A. But on the other hand, if we allow the universal machine to have oracle access to A plus a set in sigma kp, we can get better. That would imply that P is not the case level in the polynomial hierarchy. Now, if you think a little bit about that, it is reasonable, when you work this out, to try A in the polynomial hierarchy. But the results that I have shown shows that this will not work. Yes, because actually not for any A in P space, which includes the polynomial hierarchy, will not be able to get this first inequality. So I have to look for A outside P space. So do that and to show it. And that's all.
Any questions? Comments?
All the results about CD complexity for use actually hash functions. So your distinguishing program consists of 2 parts: hash function and hash value. Is it possible to use any other technique? I mean, have you any idea how one can use avoid using hash functions constructor?
Well, yeah. So Borman for now and Laplace they use prime numbers and they take multiple, but that's also
It's the same.
it's the same. Yeah, it's the same. You can use extractor, but extractor also can be viewed as a function of hash
And
functions.
also in the Sipser's proof.
Right.
So I would call it not CD complexity, but hash function complexity.
Well, yes, that's because the distinguishing program it's a fingerprint of X.
Fingerprint complexity.
Fingerprint, yeah. Yeah, so this already takes us to. If we are looking for similar results for CP complexity, I think those are hopeless. That's my.
You mean it's possible to formalize this and even to maybe to have a definition of other type?
No, it's clear how to define fingerprint complexity.
Yeah,
The program is 2-part program, hash function and hash value. And it's clear that it is always less than CD complexity.
No, okay. You can say also that just any program which distinguish x is a hash function which maps either to 0 if it's x or to 1 if it's not x. What is hash function?
Yeah, I think Sipser's definition already captures this. Somehow, yeah.
Any other question? I was a bit curious about the hypothesis in the case of P-poly, the IH hypothesis. I mean, these SAT gates, I mean, I was trying to understand how much stronger than... no, next one. Okay. Well, you went too far. Oh, yeah, it's next slide. Oh, no, sorry. Yeah, you
So this is for P-space poly.
No, the previous.
For
you're
P-poly,
right.
I need
It
a
must
function.
be previous slide.
Yeah.
Here. Okay. Computability need. Okay, but circuits with SAT gates of size 2. I mean, this SAT gates, I mean, it's completely, it's far more.
Yeah, if we
far
have
harder than what the usual hypothesis with Boolean circuits.
yeah, so without set gates, we get the assumption which is required to derandomize BPP, but here we need more than that.
I mean, I wasn't very familiar with.
No, sub gates is just just projection, yeah. What is SAT gates?
Solving an
You
empty,
can solve the SAT problem.
solve an empty problem. You know.
Yeah, so you need an NP-complete problem. You know.
Okay. So it's not connected with using SAT as an oracle of the circuit. It's not exactly the same, is it?
It's but you can play it many times. Yeah, I think it's the same. Yeah. But this is how it is formalized for circuits. Yeah.
Okay.
Use of oracles. Yeah. Yeah, basically it's oracles with circuits
Okay.
oracles with
Okay, then I take it.
Can you say what the hypothesis you need for p-space / poly is? The actual.
Yeah, here I mentioned this is stronger than what I need. I need similar, but I need circuits of size 2 to the epsilon n with oracle access to a p-space complete set. And this implies that, so this is stronger than what I actually need.
Any other question, comment? Okay, let's thank our speaker. Thank you.